Okay.
That's what happens to me. I need to go back. In Mark, it said Mark 2, but it says, yeah. I should have looked at it there. Now I have to go back. And wait, does she have the office hours tomorrow? Just let her know. Huh?
All right, I opened our class on iClicker, so go ahead and join the class and we will get started. I have a couple of announcements for you all. Yeah. 15% of your full grade, of your total grade is iClicker. We all ready? It's in the syllabus. Okay, I'm ready. We're just waiting for you all to quiet down. All right. Some announcements. So don't forget our first exam is Wednesday. It will be a packet. You can put all of your answers into the packet. You don't need to bring a Scantron. Just make sure that you bring a pen or pencil. I definitely recommend a pencil. And eraser, and then a scientific calculator. Do not bring a graphing or programmable. I did the same thing this morning. Programmable calculator. If you come here with a graphing or programmable calculator, I will take it and you will not have a calculator to complete the exam. So make sure you have a scientific one to complete the exam. There are about 17 questions, give or take one multiple choice question, but there will be 3 short answer. Those are math questions where you need to show your work and show how you reach the answer. These are ones where you can earn partial credit or full credit, but to earn full credit, you need to show your work. There's a lot more information on Blackboard in an announcement about the exam. And then the Next Achieve homework is posted, so that's due Monday at 9 a.m. This is Chapter 3, Part 1, so all about naming molecules, which we'll cover today, and then we'll finish that up on Friday. That's everything. Any questions? All right. So let's get started with Chapter 3. So Chapter 3 is all about compounds and the mole. The first half of the chapter is about the different types of compounds. So we'll talk about what's different between a molecule and a compound, and then naming molecules and naming compounds. And then the second half of the chapter is about the mole, so how many actual atoms are in a certain amount of a substance. The picture here shows 1 mole of sodium chloride and 1 mole of water. And then the chemistry cat, there's a little joke up there for you about moles. Chemistry cat, there are a lot of different memes that someone put together with this very specific cat. So if you're interested, you can find a lot of those online. So here's our outline. All the different sections, of course. We're not going to cover 3.5, naming acids. That's not a main learning objective for our class. So I don't have any slides from that section. You will learn about naming acids as you go through chemistry. And then 3.6, I don't have specific slides because this section in the book is essentially a flow chart of how to name a bunch of different compounds. So I'll show you what the flow chart looks like, but it's too big to put on a slide. And we'll talk about all the different ways to name different compounds. Not different ways. We'll talk about the ways to name different compounds in sections 1 through 4. So that's what this PowerPoint is that you all should have by now. And then the next PowerPoint that I'll post will be the second half of the chapter, so starting with 3.7. And then here are learning objectives. Same thing, you can cross out the one related to naming acids. And again, just a list to check to make sure that you are learning everything that we're meant to learn in the chapter. Any questions back there? Okay. Any questions over there? All right. So let's start with section 3.1, chemical formulas. So we will interpret chemical formulas and write chemical formulas to represent chemical compounds. We're going to start with a question. So what elements are present in the following compounds, and then how many atoms of each element are present? Just take a minute to list the elements here and list how many are present in these compounds. Yes.
Do we have to know like the groups on the periodic table?
Yes. Yeah. Okay, let's go through these. So this first compound here, we start with a magnesium atom. So we have one magnesium. Then we have, by the way, this is an L, not an I. That's a lowercase l. So we have chlorine and 3 oxygen atoms, but they're within parentheses, so that 2 subscript after parentheses applies to the chlorine and the oxygen. So we have 2 chlorine atoms, and then we have 6 oxygen. Similarly, for the second compound, we have NH4 in parentheses with a 2 subscript after the parentheses, so the 2 applies to the nitrogen. We have 2 nitrogen, and then we multiply 2 and 4, so we have 8 hydrogen atoms. We have 1 sulfur and 3 oxygens. Ooh. Okay. So these chemical formulas tell us how many atoms are present in a unit for these different compounds. So that's what we'll talk about. Chemical formulas provide the relative numbers of atoms of each element in a substance. Of course, we use our elemental symbols from the periodic table to represent atoms. And then the subscripts indicate the number of atoms of each type, just like we saw in the last slide. And then an example here is glucose, which has 6 carbon atoms, 12 hydrogens, and 6 oxygens. We can also describe the formula unit, which is very similar to a chemical formula for a compound. So a formula unit represents the ratio of atoms. Essentially the same thing. That's in a compound. And then compounds can exist in different forms. So we have molecules and we have lattice structures. Both molecules and lattice structures are compounds, but lattice structures are not molecules, and molecules are not lattice structures. So molecules is when we have an individual particle that are made up of bonded atoms, and in this case, one formula unit is one molecule. So an example of this is caffeine. This is not an example, this is sodium chloride, relevant on the next slide. Caffeine, this molecule formula is C8H10N4O2. One caffeine molecule, we say, is a particle of caffeine, and that contains all of those atoms, and this is a standalone particle. These are atoms bonded together through covalent bonding, and they're all non-metal atoms. We'll talk about covalent bonding more in a later chapter. And then these are also known as molecular compounds or covalent compounds. So these are molecules. And then lattice structures are three-dimensional networks of atoms. That are bonded together in repeating patterns. So in this case, one formula unit is one repeating unit of the bonded atoms. In lattice structures, we have a metal and a nonmetal that are held together by ionic bonding. So we have metal, nonmetal, ionic bonding, and we call these ionic compounds as well. So an example here is sodium chloride. Sodium chloride is going to be an example for a few slides. But here, sodium chloride exists in this lattice structure. And you can see the difference between caffeine. Caffeine exists as its own molecule. Sodium chloride exists as a lattice structure where there are multiple chlorine atoms and multiple sodium atoms in this lattice. And so this picture outlines a few formula units, one sodium and one chlorine atom. But you can see that they're all together in that lattice structure. But our formula unit is one repeating unit of the bonded atoms. Okay, so lattice structures, metal and nonmetal, ionic bonds, molecules, all nonmetals, and covalent bonds. We have some elements that exist as diatomic molecules. These are all nonmetals. We have all of the halogens up to iodine, so fluorine, chlorine, bromine, iodine. We have hydrogen, the first element, nitrogen, and oxygen. These exist in nature as diatomics. Di represents two, and then atomic, we have two atoms bonded together. And so we're going to talk about naming molecules that have two nonmetal atoms. But if it's the same atom, then we just call this by the atom name. So hydrogen, chlorine, bromine. Sometimes they're referred to as dihydrogen, dichlorine, dibromine. So these exist in nature as diatomics, and then other atoms like phosphorus and sulfur exist as atomic clusters. So phosphorus exists as P4, four phosphorus atoms bonded together in that shape. Sulfur as S8, 8 sulfur atoms bonded together. Okay, any questions so far about lattice structures, molecules, combinations of atoms? Okay. This one is just a quick iClicker here, one of the compounds from the first slide where we were looking at the two different compounds. Is this one an ionic compound or a covalent compound? Let's do 30 more seconds. Make sure you get your answer in. Five seconds. All right, I'm ending it now. Okay, a little bit of a mix. So in this molecule or this compound, we have magnesium. Magnesium, if you find it on the periodic table, this is in column 2. And all of the column 2 atoms are metals. So magnesium is a metal. And then here we have chlorine and oxygen, which are both nonmetals. So if we have a metal and a nonmetal, we have an ionic compound. Okay, so we've talked about covalent or molecules and ionic compounds, which are lattice structures. In this unit, we will talk about the different steps to name these covalent compounds. Binary covalent compounds, where binary means we have 2 elements. And covalent means that we have, both of these are nonmetals. So there is an International Union of Pure and Applied Chemistry, or IUPAC for short, that has created all of the different names or established all of the different names for naming molecules and compounds. Before that, scientists would name a compound that they discovered or are analyzing, and then in a different country or a different area, they might have a different name for the same compound, and then scientists can't communicate about those compounds together because they have different names for them. So we have this system to name molecules and compounds so that scientists can communicate across countries and within countries as well. So the nomenclature, or the way we name molecules and compounds, these guidelines differ slightly for molecular, or in other words, covalent compounds and ionic compounds. They are similar, but not quite the same. So this section is about molecular or covalent compounds, and then we have another section about ionic compounds. This next slide has really the 3 steps that we follow. And I have an example at the bottom here, CO, which is carbon monoxide, which we'll look at as we go down this list. So first, the element that appears first in the molecule keeps its elemental name. So carbon is first in this representation of CO, and so carbon just stays as carbon. The second element begins with a root that's derived from its elemental name and then ends with the suffix "ide." So we have oxygen. The root for oxygen is ox, and then we have "ide" as the suffix. And then when the formula contains more than one atom of a given element, the name of the element usually contains a prefix that specifies the number of atoms present. And in this case, if the second atom even just has one, we use this prefix mono. If the first atom only has one, we don't use a prefix, but if there's two or more carbons in the molecule, then it has a prefix. And on the next slide, I have all of the prefixes. No, in 2 slides, I have all the prefixes. Next slide are all the roots. So if these elements are the second element in a binary covalent compound, these are the roots that you use before I. So iodide, nitride, bromide, chloride, etc. So that's for the second element. And then if we have more than one of the first element or one or more of the second one, we use these prefixes. So we saw carbon monoxide. The mon part is to communicate that there's one oxygen. Di is for two, so silicon dioxide. We have two oxygens, so we use di. 3 is tri. 4 tetra, 5 penta, 6 hexa, 7 hepta. And then I want to talk about these down here. So all of these have one of the first atom. So one iodine, one sulfur, one phosphorus. So we don't change that first atom name. We keep it as iodine, sulfur, phosphorus. In this example here, we have 2 sulfurs and 8 oxygens. So in the name, we use di to communicate there's 2 sulfurs, and then we keep the name sulfur as it is as the element name. And then there are 8 oxygens, so we have oct for 8, ox for oxygen, and then ide to end all of the names. Here we have 4 iodines, so tetraiodine, and then 9 oxygens, non-oxide. 4 phosphorus atoms, so tetraphosphorus, and then 10 oxygens is decoxide. I also have a flow chart here of how to name these binary covalent compounds. The first nonmetal, so looking right here, if there's more than one, we do the prefix and then just the name of that element. And then the second nonmetal gets a prefix, the root of its name, and ide at the end. So for example, I have N2O here. The first element is nitrogen. There's 2 of them, so we say dinitrogen. And then we have 1 oxygen, monoxide. Mon for 1, ox for oxygen, ide, because that's how we end these things. So that's dinitrogen monoxide. Okay, let's practice this and name these compounds. So this is a clicker question. Well, this is one that's not multiple choice. You type in the name of the compound. So we'll spend a few minutes working on this. Yes.
Oh, maybe it's like, oh, 'cause it's eight. Yep. I think actually more towards the beginning. Yeah.
Yeah. They said it right there. Maybe it's looking. Yeah, there's
Let's say 1 more minute. Five seconds. All right, ending it now. So there are, we got carbon. Okay, good to see the distribution here. So this first compound, we have one xenon atom. When we have the first atom, then there's only one. We don't use a prefix. So we say xenon. And then we have 4 fluorine atoms. The prefix for 4 atoms is tetra. So we have tetrafluoride. So xenon tetrafluoride. CO2, we all recognize that molecule. I think everyone got that one right. We have 1 carbon atom, so carbon. We have 2 oxygen atoms, so we use the prefix di, and then oxide. Ox for oxygen, and then ide because that's how we end the name. And then for our last one, we have 2 nitrogen atoms. So we use the prefix now, di, and then nitrogen because this is the first atom, so we don't change the name of the element. We have 5 oxygens. So we use pent-ox for oxygen, ide, because that's how we end the name. You have a question?
It's all getting capitalized. I mean,
No.
capitalized it, but
No, that it'll accept any capitalization. Or if I need to go in and accept it, that's fine. I'm going to check these after class. Other questions? Nothing at all? How come I didn't use penta for the last one?
Because there's two vowels, there's a vowel.
There's okay, 2 vowels, there's a vowel. Only thing I want to point out, you're on the right track, but here we use, where is it? Tetraiodine. So we do use the A when the next vowel is the I, but if it's oxygen and the vowel is the O, then we drop the A. So this is, instead of nona oxide, just non-oxide.
Is it the only case we use?
That's the only case I've come across so far for when the next vowel is an O.
Would you accept the second?
The first part too. If oxygen was the first atom.
Except for I.
Yeah, except for iodine. Okay, another quiz. We're given the names now. Write the formula. We can't do subscripts in iClicker, so just write the number and assume in your mind that it's a subscript. You can't. Just put the number in. Yeah.
For letter I.
Say 30 more seconds. And let me know if you have questions. Ten seconds.
No, there's
All right, ending it. See how we did here. A little bit of a mix. All right. So this first molecule, we start with phosphorus. This is element P. And then trichloride. Tri tells us we have 3 of whatever this element is. Y'all, please, please quiet down. Thank you. Over there too. Thank you. Tri means we have 3 of whatever element that is. Chloride tells us it's chlorine. So we have 3 chlorine atoms. Next molecule, we have iodine, so element I. Fluorine, so element F, and there's 7 of them, so I have 7. Questions before we talk about different special cases for hydrogen? Okay. So binary compounds with hydrogen don't always follow. I don't know if it's the acoustics in this room, but I can hear even if you're whispering to the person next to you. That's distracting to me, but it's also distracting to the people around you. And I've asked the class multiple times to stop talking while I'm talking. I think that's it's a way to show respect to your professor. So I will still remind you if I need to, but I hope that I don't have to remind you to stop talking. Okay, so binary compounds with hydrogen don't always follow the same rules that we will talk about, or that we have talked about for covalent molecules. So they don't really have systematic names. If hydrogen is bonded to elements in groups 1 or 2, they're named more like ionic compounds, which we haven't talked about yet. But for example, lithium, or LiH, is lithium hydride. CaH2 is calcium hydride. I'll just write a note here that these are like ionic compounds. Or ionic naming, which we'll get to later. If hydrogen is bonded to elements in group 16 or 17, then hydrogen is listed first, and we name them like covalent compounds, where HF is hydrogen fluoride, HBr is hydrogen bromide, although in this case we're not using that mono prefix for fluoride and bromide. And then there are other unsystematic names for molecules with hydrogen, like H2O is just water. That's the name we have for water, for H2O. Hydrogen peroxide is H2O2. Hydrogen sulfide is H2S. You don't necessarily need to memorize all of the different hydrogen names, but you'll come across these in chemistry, so just keep in mind that the names don't follow our typical rules. And that's all for binary molecular compounds. In this section, we're going to start talking about how ionic compounds come together, how we have ionic compounds that are formed, and then we'll talk about naming the ionic compounds. So when we have an ionic compound, we always have a positively charged ion. Remember that positive cation. And we have a negatively charged ion, or an anion. So we have something that's positive, something that's negative. When we form ionic compounds, the charges have to cancel each other out, the positive and the negative, so that the compound is electrically neutral. So every ionic compound has an equal amount of positive charges and negative charges. So sodium chloride, we talked about this before. Sodium chloride is made of sodium, which is a cation with a +1 charge, and chlorine, or chloride, which is an anion with a -1 charge. So in ionic compounds, these atoms are attracted to each other with ionic bonds. And ionic compounds may not be referred to as molecules because the atoms and molecules are connected with covalent bonds. Covalent bonds are different than ionic bonds, and we'll talk about the difference in the future. And we can refer to ionic compounds as formula units. We talked about that at the beginning of this chapter. And then a little bit more information about sodium chloride. So I told you we talk about this a lot today. Sodium exists as a metal, Na, solid, looks like this as the particle view, or like this as a macro view. You're just looking at a bunch of sodium metal, that's what it looks like. Chlorine is a diatomic, exists as a gas, Cl2. Here's a particle view of chlorine gas, and it has a yellow hue to it. Sodium loses an electron to yield sodium with a positive charge. Chlorine gains an electron to yield Cl-. And then the overall charge of sodium chloride is neutral. And when they bond together as ions, they form crystalline sodium chloride. It looks like a salt. And then here's that particle view of the lattice. That's in salt. So to form ionic compounds, or to take two atoms and determine how they will form an ionic compound and in what ratio, we need to know the charges that those atoms typically make. We can use a periodic table for most of them. So with the exception of hydrogen, which isn't a metal, the rest of this first column here makes a +1 charge. And we can assume that anything from that first column has a +1 charge. We can assume anything from column 2 has a +2 charge. And that stays consistent. And then if we go to more towards the right of the table, we're looking at nonmetals. So this zigzag here, our step atoms are the metalloids. But looking at nonmetals, nitrogen and phosphorus are typically -3, oxygen, sulfur, selenium -2, and then halogens -1. I said typically, but we can assume that these are the charges that when these atoms are ions, this is the charge that they hold. We can say +3 for aluminum, +2 for zinc and cadmium, and +1 for silver. All of the other atoms have variable charges, so we cannot assume a specific charge. For example, copper could have a +1 charge or a +2 charge. So in formulas, we either have to communicate what the charge is or it's implied by what else is in the formula. We'll see examples of that. Okay, so using this information, oh, I don't have a clicker for this one. Okay, so let's spend a minute working on that. So using monoatomic ion charges, so what we know from the previous slide, determine the chemical formulas for these binary ionic compounds that are made of the following elements. So essentially, in what ratio do these atoms need to combine so that their charges cancel out? Yeah. So I look at All right, let's start to go over these. Looking at this first example, we have barium and fluorine. If we look for barium on the periodic table, it's in the second column, so it has a +2 charge, and then fluorine is in 7A, so a -1. So +2 for barium, -1 for fluorine. For these charges to cancel out, we need to have 2 fluorines. So -2 overall, +2 from the barium. So the formula would be BaF2. Aluminum has a +3 charge, and oxygen has a -2 charge. So we need to make sure that the molecule is neutral. There are a couple different ways you can do this. One is to find the least common multiple between these 2 charges, and in this case it would be 6. And then we multiply, or we give the subscript to each element, whatever we need to multiply the charge to get to 6. So aluminum, we would have to provide a subscript of 2 so that it would have a total positive charge of 6. And then oxygen, a subscript of 3 to have a total negative charge of 6. We are essentially doing the same thing in the first example, but using a 1 and a 2 is a lot simpler than for the least common multiple is 2 in that case. The other way is to take whatever the charges of the cation, so the 3, and make that the subscript for your anion, and then do the opposite, charge for anion, make that the subscript for the cation, and that would give you Al2O3. Sometimes in that case, you'll get numbers like 2 and 4. If the numbers are 2 and 4, then you have to reduce that down to 1 and 2. Both are accurate methods. And then our last example, copper is one of those atoms with a variable charge. Sulfur is not. Sulfur has a -1 charge. So to have the positive and negative charges cancel out, we need 2 coppers and 1 sulfur. Yeah. This is what I did. Yeah. Okay. Questions on any of these formulas? Okay. So there are also some ions that we call polyatomic ions. So it's a group of multiple ions bonded together. And they're common in molecules, so we give them a name for the specific ion. So in this case, NO3- is a common anion. We call this the nitrate anion. This is a group of 4 atoms bonded together. They're bonded with covalent bonds, but they have a charge. And so we consider them an ion, so a polyatomic ion. Most of the polyatomic ions are anions, but there are 2 important cations, the ammonium, which is NH4+, and then hydronium, which is H3O+. Then on the next couple slides, I have tables of a bunch of different polyatomic ions. You don't necessarily need to remember or memorize all of these names. The first 2 are important, hydroxide, OH- and cyanide, CN-. And then I'll let you know if there are others that you should memorize. When you're doing the homework for chapter 3, you'll need to look at this chart or this table to identify the name of a bunch of different polyatomic ions. So on this slide are all of the ions that have a -1 charge overall. And then on the next slide, we have ions with a -2 charge, -3 charge, and then the 2 cations at the bottom here, ammonium and hydronium. So let's do this learning check. The first one I will push as an iClicker. We're writing the chemical formula just like we did in the first, or not the first, the last example that we did, like BaF2, Al2O3. Write the formula using chromium +2 and SO4 2-, the sulfate polyatomic ion. if you have more than one polyatomic ion, then it belongs in parentheses, just like these. You didn't know it, but at the beginning of class, you were looking at molecules of polyatomic ions. This is magnesium with the polyatomic ion ClO3-. There are two ClO3- polyatomic ions in this molecule, so the whole ion gets parentheses and then the 2 goes after. And that same thing, that's the cation, ammonium, in parentheses with the 2 subscript. Yes.
So for like, when you're doing the coefficients versus like the subscripts,
Let me come over there in a second. Let's do like 1 more minute, and we'll go over these two. Okay. This is the correct answer. So I guess if you do this, we need to know that so these are if it's one chromium and ions.
So you write it like that. Oh.
All right, 20 more seconds. All right, ending it now. Make sure your answer is submitted. Okay, so for this first grouping of ions, we have chromium with a +2 charge. This is an atom or an element that can have variable charges. So chromium with a +2 charge, and then the sulfate polyatomic ion with a 2- charge. These cancel out, so we write the compound as CrSO4. And that's it. Oops. For the second one, we have chromium 3+, and then a polyatomic ion with a 2- charge. We have to do the swapping of charges to get the subscripts or finding the least common multiple. And in this case, we need 2 chromium plus 3 atoms, and then 3 of this polyatomic ion. So now we use parentheses with the 3 subscript, yeah.
Yeah, so for the first one, for SO4, would we not put it in parentheses separated?
Right, so no parentheses are needed if there's only one polyatomic ion in the molecule. I'll accept it today, but in the future it's wrong. All right, thanks everybody.